Hello everyone, this is Hao from Tohoku University of Japan. The topic of this presentation is an efficient skinny matrix multiplication method by folding input matrix into tensor operations. NVIDIA's Tensor Core unit is introduced in Volta and Turing architecture to accelerate mixed precision matrix multiplication. As the figure shows, a tensor operation performs A multiplies B and plus C, where A and B are half-precision matrix, C and D are single-precision matrix. The latest QLAS library can provide a high performance for mixed precision matrix multiply when all dimensions of the input are large. However, it does not have an ideal performance when inputs are tall and skinny. Therefore, this work aims to optimize the computation of a transposed matrix A multiplying matrix B. Both A and B are tall and skinny matrices. The challenge here is that if the size of m and n dimensions of an input are smaller than that of a tensor operation, the computation for tensor operations cannot be fully used. Another challenge is that how to properly map the computation tasks to the thread blocks and threads. To optimize the utilization for tensor operations for skinny input matrix, we can load multiple segments into a tensor operation. This is implemented by rearranging the layout of a fetched segment in the shared memory, as shown in the figure, just like folding the input matrix. Then multiple segments can be loaded into a tensor operation, and more computation can be used. The computation is parallelized over the k dimension, and the computation tasks are assigned to different warps in a kernel. Each warp has a buffer in the shared memory, and in each iteration, a warp fetches a segment from each input matrix and performs a tensor operation. A warp only consumes data fetched by itself, so there is no need of synchronization between different warps within a thread block. For different input size, we always set the number of thread blocks to the number of streaming multiprocessors on a GPU, and adjust the number of warps and the number of folding segments depending on the input size. As the experimental result shows, the optimal configuration can be changed for different input size, so we always select the optimal configuration based on the input size. And the experiment of this work is conducted on a RTX 2080 Ti GPU, and QLAS 11 is used for comparison. In current implementation, the size of tensor operation is set to 16 by 16, which means the proposed method is applicable only when m and n dimensions are no larger than 8. When the k dimension is set to 2 to the power of 14, the proposed method can achieve 1.71 to 2.7 times speed up compared with Q+. Except the case of 1, the speed up gets higher when the size of m and the n dimensions are smaller, because more segments can be folded into tensor operations. And when the size of k dimension is set to 2 to the power of 20 in the figure B, the speed up gets lower when m and n are multiple of 2. This is because QLAS has optimization on memory access for those cases. In conclusion, this work proposes an optimization method for skinny matrix multiplication on GPUs. With proposed optimization method, the implementation of this work can achieve a significant speed up compared with the latest QLAS library. For future work, we would like to further optimize the implementation of memory access, and we are also interested in designing efficient kernel for other type of inputs. For example, the multiplication of a tall and skinny matrix by a square matrix. Thank you for your listening.